In this video, we'll apply integration to compute the volume of a solid region. So suppose the solid region extends in the x direction within an interval from a to b, like in this diagram here. To set up the integral, we'll first subdivide the interval into little subintervals, as usual. And then we'll choose one of these subintervals, mark off a point, call it xi star, and then we'll look at the cross-section in this interval. So here I've drawn in the cross-section, right? So because we're working within an interval, this cross-section has a small thickness, and then this is the side of the slice is a cross-section. So if you think of this solid region as a loaf of bread, this cross-section looks like a single slice of the loaf. So the idea here is to first compute the volume of a single slice. So the volume of a single slice would be the area of the cross-section times the thickness of the cross-section. So suppose the cross-section has some area given by the point here xi star. So let's call it A of xi star. So typically the area of the cross-section is going to vary as x varies between A and B. And then the thickness will just be delta x. So this is the volume of single slice. So to get an approximate volume of the entire solid region, we add up the volumes of the individual slices. So suppose there are n of them. And so this is an approximate volume. So as we take more and more subintervals, the approximation gets better and better. So in the limit as n goes to infinity, we'll get the actual volume. And so this limit can be computed as the integral from a to b of a of x dx, where the function a of x again represents the cross-sectional area. Okay, so now let's try this method of slicing to compute the volume in an example. So let's scroll down. So in this example, we're asked to find the volume of the solid whose base is the region bounded by the semicircle, given by y equals square root of 1 minus x squared, in the x-axis, and whose cross-sections through the solid are squares. The solid in this problem is pictured in the diagram to the left here, and in this picture the cross-sections are a little bit easier to see. So you can see that the cross-sections vary as the cross-sections move along the x-axis, and it's described by this function y equals square root of 1 minus x squared. Okay, so let's first set up the integral to compute the volume. Right, so in the method of slicing, the volume is given by the integral from a to b, and the function we integrate is the cross-sectional area a of x dx. So what we want to do is first figure out what the cross-sections are. So in this problem, the shape of the cross-section is a square. So we have square cross sections. So we need to figure out a formula for a of x. Again, so because the shape of it is a square, the area of a square is just s squared, where s is the length of a side. So in this case, what is the length of the side? So the length of the side is this distance here, but it's just given by the function square root of 1 minus x squared. So a of x is the square root of 1 minus x squared squared. Right, so again, the side length is given by the function. So simplifying this expression, the formula for a of x is, so the square cancels out, so a of x is just 1 minus x squared. Now the other thing to do is figure out the endpoints of integration, so the values a and b. Right, so these values here, so these points are just where the function intersects the x-axis. So we just need to solve the equation y equals square root of 1 minus x squared. So the x-axis is when y equals 0. So plugging 0 into here, you get 0 equals square root of 1 minus x squared. And then solving for x, so squaring both sides, you get 0 equals 1 minus x squared, or x squared is equal to 1. Taking the square root, you get x equals plus or minus 1. Right, so this point would be at minus 1. This point would be 1. So this is where we integrate from. So now to compute the integral from minus 1 to 1, a of x is 1 minus x squared. And so this integral computes the volume. So just taking the antiderivative, the antiderivative of x is x minus x cubed over 3, evaluating at the two endpoints. So plugging in 1, you get 1 minus 1/3. Plugging in minus 1, you get minus 1 minus a negative 1/3. So this is just 2/3 minus a negative 2/3. And so the total is 4/3.